So let's take a look here at example 2. A slot machine at a casino randomly rewards 15% of the attempts. So every time someone plays, right, there's about 15% chance that they actually say hit the jackpot. Now assume that all attempts are independent. So what happened on the last, play of this slot machine doesn't affect what happens next. And you plan to play the machine until you earn a reward. You're determined. You're going to sit there all night if it takes that long. Now we're going to try to ask some questions about this. And I can see here that I'm going to have a lot of probability questions coming up. So if this was a question on some sort of an assessment or like an exam, what I would want to be thinking first is how does this fit in to the flow of the formula sheet? So if I go to the formula sheet, the first thing again that I always have to do is to think about what's the random variable that's going to be in play here. Then I'll progress to thinking about what distribution fits best. I can check that by seeing if my checks are met. Then I'll find the important parameters, and then I'll finally go to my calculator. So let's see how we progress through that here. So, oh look at this, part A even asks me, what is the random variable for this problem? Well, one of the things that I could easily see here is that I'm really trying to determine, ultimately, how long it's going to take before I earn this reward. So maybe I could state this. How about we let X represent the number of plays it takes to earn a first jackpot, right? Our first reward. That's what we're really interested in, right? How long do I have to sit here and keep pulling this lever, if you will, or pressing a button before I can actually get the jackpot? Now, again, when I see that I'm interested here in this kind of first reward, that's a good tip-off that I might be working with something geometric. But of course, if I want to test that it's geometric, I better also check the conditions. So let's work through this. In this scenario, every time I pull the lever, are there only two outcomes? Well, yeah, because I either get the jackpot or I don't. Okay, so two outcomes, check. Are the trials independent? Well, yeah, the question even said that, so that's checked off as well. The probability of success is supposed to be the same from trial to trial. Well, yeah, that doesn't seem too bad because the chances of winning is going to be 15%, and that's all the time. Now, what you may have noticed when you looked at these checks is that aren't checks 1, 2, and 3 here the same as checks 2, 3, and 4 for binomial? They're almost the same checks. So how would I tell this apart from a binomial distribution? Well, it has to do with that discrepancy in this first check here in binomial. In a binomial experiment, we always had a fixed number of trials. A fixed number of people were going to try to sign up for a credit card. A fixed number of questions were, say, going to be on an exam. A fixed number of rolls of a die were going to be done. And so in this scenario, we could see, do we have a fixed number of trials? Are we definitely going to sit down at this machine and only pull the lever or press the button a fixed number of times and then walk away? No. We're going to be doing something that might indicate that we have more of a gambling problem. We're going to play until we win. We don't know how long that could take. That could be on the first try or maybe on the 10 millionth try. Who knows? So this doesn't meet the criteria to be a binomial distribution, but we can easily say here that X has a geometric distribution. It seems to fit all of the checks. Okay, so now I've established that I'm in this column here. Going down to the next box, I see that I need to find my important parameter, which here is P. I'll also be able to find mean and standard deviation later when I'm asked for them. So let's see, P. P is my chance of winning, so that should be 0.15. Perfect, so I have all the information I need to get started here. So let's take a look. What is the probability that our first reward occurs on our fourth trial? So X is the number of plays it takes to earn a first jackpot. Well, in this case, I'd be looking at that being 4. I want to know what are the chances that this is equal to 4. Well, the interesting thing here is that I can still imagine a table kind of being shaped up over on the side. Even though I'm not going to fill it in, I can still imagine that I'm going to have x's and p of x's in my table. I may require one pull of the lever to win, maybe two, maybe three, maybe four, maybe five. I mean, maybe on and on and on. I don't really know how long it's going to take, right? But what I can see here is, I just want the probability across from 4. And since I'm in a geometric distribution, I will use a geometric PDF. Now, I know, according to what I have on the previous page, that my inputs here are supposed to be the value of p, which is 0.15, and then the value of x, and I want to win when x hits 4. Now, I'm going to go to the calculator here to see how I can actually try to compute this. Let's take a look. Okay, so on the calculator, I would click on second, I'd go to my vars, I'd scroll up, and you'll see that actually right at the bottom I have these geometric PDF and CDF. I want the PDF, and notice it's going to ask me for my value of p and my x value. This should be exactly what I have written down on the page, and again, what you're always required to write. Then when I hit enter, boom, it tells me my value, 0.0921. So I would say 0.0921. There's about a 9.2% chance that I win on my fourth try. Well, take a look. I can keep doing this with a lot of other questions. What is the probability that my first reward occurs in 7 or less attempts? So the number of tries it takes to get my first jackpot will be less than or equal to 7. Okay. Well, I should be able to see that's going to require that I'm going to grab a lot of values off this table and their matching probabilities. So I'm going to do a geometric CDF. Notice again that CDFs start from the lowest value in the table and they go down to a specified stopping point. Since I want all the numbers that are less than or equal to 7, I'm going to stop here at the value of 7. Perfect. So once I have this written down, I would type all this into the calculator. Let's see what we get. Click on second, go to my geometric CDF, 0.15 and 7. And I get a value of 0.6794. 0.6794. All right, let's take a look at part D. What is the probability that your first reward takes over 7 attempts? Okay, probability that x is greater than 7. So technically that would kind of be like all the values in the table, I guess that would be like 8 and up, right? Those are the values that I'm interested in. Everything below that I don't really care about. Well, if I wanted values like that, notice that's values like over here, then the values that I'm not interested in are the values that are 7 and below. So I could get this by doing a 1 minus the probability that x is less than or equal to 7. Notice that means that I can do a 1 minus a, oops, that looks a little sloppy, but 1 minus a geometric CDF of 0.15, comma 7. And if I crunched all this out on the calculator, notice that's really just 1 minus my previous answer, and I would end up with a value like 0.3206. So again, in all these questions, I can still hear that kind of common rhythm of what a geometric question is asking. What are the chances that you get your first reward on this try, your first reward on this try, your first reward on this try? That's what a geometric question sounds like. Now note that part E doesn't quite sound like this. What is the probability that you get 3 rewards in 10 trials? This is strange because it's not a geometric question. I can't use a geometric PDF or CDF to help answer this because actually here I have a completely new random variable. I'll state here this is not geometric. We need a brand new variable. Notice here the question is really, if I play this slot machine 10 times, what are the chances that I win 3 out of those 10? So really what I want to know here is if I had a new random variable, let's call it y, we'll say that we'll let y represent the number of wins or rewards we get in 10 trials. Now, if I was to go back to my formula sheet, and let's go and switch over to that now, then I could see that in the geometric column, I know I can't be there because I'm saying that I'm only going to play the game 10 times. I'm only going to play this slot machine 10 times. But if I look at the binomial distribution, that actually can account for a fixed number of trials. What becomes interesting here is that this geometric distribution is always kind of interested in a first success, whereas my binomial distribution is interested in getting a number of successes out of a number of trials. So like a number of wins out of 10 attempts. Let's check though to make sure that this actually would be a binomial distribution and a binomial question that we're now dealing with. So I know I have a fixed number of trials. Are there still only two outcomes? Yeah, I still either win or lose. I get a success and get the jackpot, or I don't. The trials are independent, and the probability of success is still that 0.15. So I can state here that y has a binomial distribution, specifically with a value of n being 10 and p being 0.15. Notice again, I'm just following exactly what the formula sheet would require. I'm thinking about what the random variable is, thinking about what distribution it has, checking that to make sure, writing down my parameters, and now I'm going to think about the calculator command that I need. Notice I'm interested in calculating the probability that y, the number of wins I get in 10 tries, I want that to be 3. Well, that could be then addressed with a binom PDF, where I have 10 trials, a 15% chance to win, and I want exactly 3 successes. If I was to go type this into my calculator, and you can go ahead and try that on your own, hopefully you can confirm you do get a final answer of 0.1298. So this is kind of alarming and can be jarring for some students at first, is that we notice that these columns aren't necessarily always going to be occurring in completely separate problems. Sometimes different parts of the same question might ask you things that are binomial or geometric, all kind of jumbled together. The key is to think about what the question is asking. There's no greater shortcut than that. If there was, I would tell you. So the best way to try to go ahead and to figure out if this is geometric or if a question is binomial is to think about what these different distributions are trying to account for. Geometric is trying to account for a first success, and binomial is trying to account for a number of successes out of a number of trials.